Okay, so today we're going to work on the PE-COFF file format stuff some more. I'm going to do a little review in a minute of how far it's gotten and what's going to happen today. Well, mostly I'll figure out what's going to happen today on the fly. But as a reminder, if you're checking this out for the first time, or if you've been seeing it, all of this work is funded by people who choose to come here and go to mrforth.com/membership and pick one of the options to become a supporter or a member. And I think there are some cool benefits. You get to see like what I'm working on more rapidly. And if you become a member, you also get access to my video library through the indexed Sonera system, which is really cool if you've ever seen it. Maybe I'll demo that again sometime. You got to log in with your membership account, and then you can see that. And you can also look at the code that I'm writing today. A lot of it ends up right here on Mr. Forth Git in the membership organization. So you get access to all that just by becoming a member, and you also keep me able to work on projects like this. Now, the project I'm working on today is the PE-COFF file format parser, and if we want, we can take a look at what it looks like right now. It's just kind of a dumper right now. You put in a file. I can put in EXEs, DLLs. I can put in object files. And you'll see here, like, it knows this is an object file, and then it dumps out the COFF header, it dumps out the sections in that file, and that's all we get in an object file. With DLL here, we get more, because we've got the extended header, we get the directory list, we get the sections for the file, we get the exports, we get the imports, and we also get exception handlers. All of this is here living in the information stored in this directory table. So we're going to keep going through the directory table stuff for now. There's other stuff to do on the object file side, but we're focusing on the binary file side right now. And the binary file has a lot of interesting stuff stored in these directories. So I've done this and this. We skipped resource table because we don't have an example of it. I think we could make an example of it if we grabbed an exe with like an icon or something. Anything that uses resources, we could go in there. That's a little bit more niche. Certificate table, we don't have an example of that, so I'm not going to parse it. Relocations, so that's more interesting. We could work on relocations. Debug is a very simple one. I already know that. TLS table, I don't know exactly what that does, but it'd be maybe good to know. Load config table might be interesting to look at. And I don't know what IAT stands for off the top of my head, but that looks like it's got some amount of size to it, so possibly worth checking out. But let's start with checking out base relocations. So base relocations. Okay, so that's just a flag. Base relocation table. Okay, here we go. This is the list of directories. And boom. The base relocation table contains entries for all base relocations in the image. The base relocation table field in the optional header directories gives the number of bytes in the base relocation table. For more information, see, the base relocation table is divided into blocks. Each block represents the base relocations for a 4K page. Each block must start on a 32-bit boundary. Okay. The loader is not required to process base relocations that are resolved by the linker, unless the load image cannot be loaded at the image base that is specified in the PE header. Right, base relocation block. Each base relocation block starts with the following structure. Okay, here we go. So we've got two 4-bit integers, it looks like. Page voff and block size. The total number of bytes in the base relocation block, including the page RVA and block size fields, and the type offset fields that follow. Okay. The block size field is then followed by any number of type or offset field entries. Each entry is a word and has the following structure. 4 bits for type, 12 bits for offset. To apply base relocation, the difference is calculated between the preferred base address. Okay, cool. I get the idea. So we're going to have base relocations. The image base plus the RVA is added to each offset to create the VA where the base relocation must be applied. Okay. Got it. So this is going to be our page VOFF. And this is going to be the total number of bytes in the base relocation block, including the page RVA and the block size fields, and the type offset fields that follow. The total number of bytes in the base relocation block. Base relocation block. Okay. And then we get these 16-bit integers that are the type and offset. Base relocation type offset. Right? Like that. And then we've got all of these right here. Let's see. So we have two different cases for 5. Base MIPS, base ARM. Right, okay. This relocation is only meaningful when the machine type is RISC-V. The base relocation applies to the high 20 bits with 32-bit absolute address. Reserved must be 0. Reserved must be 0. 6. Reserved must be 0. I don't think that's what you meant. I think you meant it should not be used or something. The relocation is only meaningful when the machine type is RISC-V. Okay, so there are a couple ways I could approach this, right? I could just say, let's collapse them down so we only keep one. But in this case, like, and that's what I would do if they were like redundant names for the same idea, which happens sometimes. But that really wouldn't work here because these are not redundant names for the same idea. These are separate names, and I don't want to lose any of these. Another thing I could do is I could create a table. I could create my table to look like this. It would have the name, the architecture, and then the code, right? So instead of, normally I would just do the name and then the code, but here I could say, put down the architecture. And then the idea would be like, maybe if I put a 0 there, then it applies to all architectures. But if I put down an architecture field, then it applies just to that one. But then I have cases where there's like this one here applies to arm or thumb. So then it's like maybe I need a flag field, and then I'm going to be putting all the flags in for all of these, and then not for that. So that's an option. But there's only 5, 7, and 8 that actually need to be different for each one. So another approach here is I could make one for each architecture, right? So I could say, all right, this is cool. I'm not going to use all of these. I'm going to make base relocation type offset, or base relocation MIPS, right? And base relocation, well, we could go base relocation type offset, and then we would have define PE base relocation MIPS X list, right? Put down the X, and then it's just name, code, over and over again. And then we get another one, and this one would be like our arm, and then get another one, and this would be our wrist, and get another one, and this would be our thumb or whatever. Also have to figure out like what is and the weird thing about doing it that way is that, like, you know, if we look at I386, which is the x86, which is the name for x86, or if we look at AMD 64, which is the name for x64, over here in base relocations, there are no special case, like it doesn't appear here, so 5 just means nothing, I guess, on an x86 64. Thumb, risk V, long 32, long arch 64, like none of these apply to this particular architecture that I'm on. So it's a little unclear what the best way to write down the map is here. And like, yes, we could go with the machine type codes, and it's just there's a lot of them. I'd have to list out a bunch of machine type codes, and they're not organized here to make nice flags or anything, right? I can't just bit shift by these numbers to create flags. They're not already flags the way they're organized. There's no easy way to use these directly in the mapping either. So I'm thinking the best option is going to be to actually go to the original idea, but then add in a helper function to differentiate the special cases or something. Maybe we could do something like this. Right, and then let's finish up here. So you're out, you're out, you're out, you're out, you're out, you're out. hold on. Let's do that way. Let's line up our numbers here. So what I want to do is well, let's take out image rel based. That's cool, but it doesn't finish the thing. Let's do 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Up. Boom, 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 boom. Okay, now for these ones that are duplicates, what we'll do is we'll combine them into just something that's like split 1 or something like that. This one will be called, and then what we'll do is we'll go make some notes down here. Split 1 goes MIPS jump batter arm mov 32 risk v high 20. Split 2 goes thumb mov 32 risk v low 12i. Split 3 goes risk v low 12s long arch 32 Markele long arch 64 Markele. I don't know why those have to be distinguished actually, but there we go. All right. So that's our type offsets, and you'll notice these are the first 4 bits. So I think that means the low 4 bits, and then the next 12 bits are the 12-bit offset from here. So this is 12 bits, which means it can be anything between 0 and 4095, which is why our blocks have a 4K page offset to begin with, right? So this 12 bits gets added to the VOFF from this to actually calculate the total VOFF. And this is cool because that means instead of using 32 bits for each VOFF here, they've got it down to 12 bits for each VOFF, and they can pack it in like this. That's a cool idea. So let's put down some helper there. BE base relocation type offset get type is X and OXF. Define PE base relocation type get offset get off, let's call it. Shift off 4 bits and keep the rest. Okay, that's a good initial sketch. I'm actually going to take my first 5-minute break right here. I'll be right back. There we go. I'm back. That was a little funny. Let's put this down here so that doesn't happen again. Thank you for letting me know I was muted. Had a little misclick on OBS. So I'm trying to parse out the base relocations. And what's going to be funny here is, like, how do I want to parse them out? All they are a series of these blocks. I don't want to mix the parsing in with the printing, but what should the parser actually output that would help? I could count the base relocations, but to iterate them, I mean, it's just a bunch of blocks of U16s, right? It's a little bit hard to come up with another data structure that's going to seem reasonable for that. I mean, we could turn it into an array of types and offsets that are expanded. So it comes in with the small packed 16-bit version, and we would expand it to having 32-bit offsets and 32-bit types or something like that. So it's just a standard old C style type at that point, and we could access both parts without thinking about the blocks anymore. I guess we'll do that, because even though it's not exactly ideal sounding, it is just to give us a way to write out the dump code. So this doesn't actually have to be the final way the parser works. You know, we might just end up rewriting parsing code for this particular type of data every time it comes up. But at the very least, whatever I write here isn't what I have to keep. All right, so we want to extract the directory like we usually do. This time we're looking for the base relocation table. All right, and we are gonna want like some kind of iterator pointer that can start at the loaded data dot string plus dir voff. Was there no test here and exception handlers for? Should probably run the fuzzers on this to avoid that kind of mistake. So this would do the same sort of thing. Make sure that the voff range is actually going to be inside the loaded data range, and then we do opal, one pass last, is putter plus dir size. Okay, so there's our iteration range, and what we're trying to figure out is how we're going to pull out all of that. So that's going to be like, and another problem here is we don't know what the count is going to be right up front, right? We have a size. The size doesn't tell us exactly what the count is. What we could do is we could use the size to estimate the count. And that's going to be the dir size divided by 2, right? We could have one relocation for every 2 bytes, except that there's going to be a few headers, so we're going to overestimate a little bit. But we don't know how many headers there are, so we're just going to do this because this is an estimate that is guaranteed to be big enough. And then we're going to go PE dump base relocations. Oops, we already have that. Relocations equals push an array onto our arena of base relocations count estimate. And then we're going to begin the loop. So the loop is going to go like this. First, we're looking for a relocation block. If putter plus size of base PE base relocation block is greater than opal, then we'll break. So safety check and end, otherwise grab the block. Then the block gives us the block size. Putter plus block size. If block opal is greater than opal, block opal will just be opal. We'll clamp it. If we then do putter plus equals the size of the block, so we get past the block spot there. Another way to write this would be, let's make it U8 block plus 1. So it's based off of that block spot. We want to go to the thing after the block. And then we want to do block opal minus putter divided by 2. That is good. For each of these, what we're going to do is we're going to go, we're going to have a PE dump base relocation relock putter base relocations. Relock putter type equals PE base relocation type offset get type. Here's our type offset, found by reading from there. And we're now guaranteed that that's safe, because if that were past the OPL here, then our block OPL would be small enough that the count wouldn't allow you to reach that point, right? Like, this should be the right limiter to make sure that this is always valid, because of the relationship that block count has to block opal has to opal. block v off, page v off plus off. Okay. Relock putter plus equals 1. Okay, so that should do all the parsing, and when we're done, the actual base relocation count can just be calculated by taking the right pointer we're using and subtracting the base of the array. And then we can do arena put pop amount arena, let's see, size of base relocations times at count estimate minus base relocation count over estimate count. So we take the count of how much we overestimated, the estimate minus the final value, that's the overestimate count, and we multiply that by the size of a base relocation, and that's how much we can put back. Okay. And then if that's working, we can dump out our base relocations. All right, now we need to turn the type code into a string. That's going to be through something like this. Straight from type, base relocation type, PE base relocation type, PEH base relocation type xlist, type def, I don't know, U32, it's really like define x and c, PE base relocation type n, equals C. PE base relocation type X list. There we go. Something like that. Type base relocation type X list. Boom, boom. Whoa, okay. That doesn't look good. That doesn't look good at all. It's a lot of absolutes when that should be, like, basically non-existent. And, well, that's so many. That's so many. I mean, it's not that that's necessarily wrong, but that's 80,000, like, that's almost 80,000. No, that's almost 81,000. It is more than 80,000 relocations. Let's take a look in Remedy. Okay. Yeah, we want to see Mr. Fourth Base DLL, please. Data directory 16, so we get base relocation table. And there we go. So this is giving me a count estimate of 812. The size of the directory is just 1,600 bytes. All right, so we get that we can't have more than 800 of these. We should definitely not be having 80,000. What does our block look like? Page v off looks reasonable. Block size looks reasonable. Okay, block OPL is good. Putter goes there. Block count. Okay. So a couple things are popping out at me. Block count's a poor name. This is like a relock count. And there's nothing here doing the putter plus equals 2 that it should be doing. Okay. So that gets us to there. So yeah, that, the high 4 bits, the low 4 bits are 0. The one type we saw besides absolute was split 3, right? That was the only two types we saw. So just a little investigation here. Yeah, that's an 8. So I think we know what's happening. Do you see what's happening? I must have, these are not the, it's not the right bits. I didn't get the right bits. I think maybe the high 4 bits is the correct idea. So this is the high 4. And this is the low 4, or the low 12. Okay, now it makes more sense. Yep, that makes sense. Okay, I'm gonna guess that that's probably about right. I mean, it looks exactly like what you would think of that wanting to look like. So the only possible flaw is there is another rule I have ignored, which is that this has to be aligned on 32-bit boundaries. So what we want to do is say, at the end of all of this, let's hard calculate where putter starts for the next iteration. Right, so here we get a block, and then, so we look at block, scan relocks, put putter on next block. So what we're going to do to accomplish that is we're going to go if block size, or let's do U32 next block off equals block size plus OX FFFF. So no, that's not right. Plus 3 divided by 4. Right, so this or and not OX3, something like this, right? So this is rounding up to a multiple of 4, right? We've got, I think I have a macro for that. Align up POW2 block size 4. Isn't that what that macro is for? Yeah, that's what it does. Okay. So, if this was already a multiple of 4, this just comes back with the same value. But if it were a multiple of 2, so saying like, hey, we had an odd number of relocations or something, it would get us back to a multiple of 4, which is a multiple of 32 bits. You know, a multiple something, an offset that's 4 bytes, it's 32 bits, right? That's what we're trying to align to. And then our new putter value is just U8 star block plus next block off. And I think that won't change anything because it looked like everything was reasonable anyways, but I think it's a more robust way of doing the iteration in case we ever see files where there's not padding. Oh, which maybe I did it wrong though. Oh, I know what I did wrong. This is a cast. That needs to look like that. Right, okay. So this is back to being about roughly 800, which is what it should be. All right, how are we doing? Guess it's time to look at what directory comes next in the list. Base relocation table. Debug. Okay, great. Debug's a super easy one. I've done this one before. It's not the .debug section. It's here. Data directories. The debug data starting address and size. So image files contain an optional debug directory that includes what form of debug information is present and where it is. This directory consists of an array of debug directory entries whose location and size are indicated in the image optional header. The debug directory can be in a discardable.debug section if one exists, or it can be included in any other section in the image file, or not be in a section at all. Each debug directory entry identifies the location and size of a block of debug information. The specified RVA can be 0 if the debug information is not covered by a section header. Alright, so we want to spell out this struct real quick. Debug, what do they call it? Debug data. Data, just go back to data directory index, xlist. Yeah, it's just called debug. Okay. We don't need the headers. Here. Just try to make a struct here. Debug directory. Characteristic reserved 0. Timestamp. Version major. Version minor. Type. Size. VOF. FOF. So 44224444. 44224444. Good. PE debug type xlist x. This is going to culminate in a PE debug type U32. Live right here with the classic PE debug type n equals c undef x PE debug type xlist x, and then defining the xlist goes like this. We go undefined. Okay. Crypto hash. Embedded image debug type can go away. Very good. And so then let's go ahead and do the string 8 for that. Okay. Now the parsing. Parse debug. Again, it's a little bit weird. Don't know. I don't know what the final output data for this should be. But let's see. We got... What exactly did it say we're going to find? Are we just going to find the list of debug directory structs? Image file contains an optional debug directory that indicates what form of debug information is present and where it is. The directory consists of an array of debug directories whose location and size are indicated in the image optional header. The debug directory can be in a right. Okay. Okay, so I'm thinking we just have an array of these from the data directory based on what they're saying. It's not 100% clear, but I'm thinking that's what they're trying to say. So I think we could just start. You know, this might not be the final thing we actually would want, but I think we could start with this. And so here, what we're doing is really trivial. We're just taking a pointer into the data exactly as it is. Debug directories. Okay, these are slightly more full than some of the other structs I've done, so I'm not going to do it all on one line. Timestamp equals %u, comma, debug dir timestamp. Version, major, minor. Type. Type string. Type string. String 8 type string equals PE straight from debug type. Debug type. Debug dir type. Right? Yeah. We got here size equals percent $sign u. The $sign tells it to give it a memory size suffix. Size v off ox percent u debug dir v off f off f off dump results. All right, we've got 1 2 3 4 5 6 7 8 9 10 11 12 13. There's a lot of errors, and this doesn't look right. This can't be right, right? That can't just look like. We're getting versions, we're getting unknown types, we're getting error types, we're getting sizes all over the place, really strange offset values. Yeah, this is garbage. Okay, so this isn't what it should look like. Oh, base relocation count is totally wrong. We want debug directory count. Maybe that will explain it. Boom. Okay, so for this one, it looks better. This is almost believable. This is believable. This is believable. This is believable because it matches this. Why would it have an error type? This matches this. These look believable. These look believable. I don't entirely know how to take this. Because these look almost like coherent, except that the type information on those suggests that we're getting a debug type that is bogus or that isn't documented or something, which is interesting. So let's say we want to see this in the debugger. Debug directories, comma, debug directory count. Type 2, type 12, type 13. Okay. And here, yeah, type 12 and 13 aren't defined. And 11 also aren't defined. So these might be undocumented but real in-use codes, 12 and 13. Which is interesting. Let's take a look at this in another angle. Okay. F off 180580. Wait a minute. This file's not big enough for those offsets to exist. One 80520. I don't get to a point where I have 6 digits of six hexadecimal digits. So the thing is, these all seem reasonable, but they can't be. See, this has 198 kilobytes. Let me just check something here. 198 kilobytes. 98. In hex, yeah, that gives you these 5 digits here. You can't have an offset this big. 180520 doesn't fit because we only go up to 31800. You know what I'm saying? Do you see what I'm saying? And we are doing Mr. Fourth Base DLL. You hang out. You're helpful still. Ah. Well, that matters. Okay, there we go. Now, we can come in here and we're looking for 2C1964. Well, 2C 164. 2C160, 2C164, 20 bytes. Here's 12, 16, 20. That doesn't mean anything to me. 0, C7, C7, 2C170C6. 2C178. 2C178. 768 bytes. 2, 3, 4, 5, 6, 7, 8. 3. It doesn't tell me how big my selection is here. But 768, this is like going 16 at a time. 1, 2, 3, 4, 5, 6, 7, something like this. Possibly a little more or less. I've got nothing. Now that first one, 2C128. For 60 bytes, so here's 8, 16, 24, 30, 8, 16, 32, 48, 64, 1, 2, 3, 4. So that I don't know what the first part is about. RS 2C128. Let's take a look at what it says here. I mean, it's pretty clear the second part is the path to the PDB. That part is clear. I don't know what to make of the first part. It's about, well, it's exactly 24 bytes long. One 13969867006. No, it does not match the timestamp. It's not UTF-8. Huh. It doesn't really look like UTF-32. I mean, until that null character, they're all valid UTF-32, or UTF-16, I mean. If it was UTF-16, that would mean that it's got a bunch of Chinese characters or something right before the PDB name, which would be very strange. '21, 2014, something like that. I'm just looking for, like, is there a timestamp in here? For today's date. But it doesn't look like it. Okay. So I think could it be a GUID? It's 24 bytes. Is that a GUID size thing? I want to look at another executable or something. C780. Starting right here. RSDS2. From there to there. So it's exactly 24 bytes again. The second one and the first one both start with RSDS, which is interesting. This one starts with RSDS and then changes from the previous one. It also happens to directly contain PDB dot I, which is interesting. But it looks like they're both exactly 24 bytes. Why would it be off by 24 bytes? What am I missing? Why would you be off by 24 bytes? The total size of the section is 54, so it contains all of this. That's 16, 32, 48, 50, 52, 54. So yeah, it contains 24 bytes plus the string we actually want. Well, here we get some names for the missing symbols. The missing debug info types. Cool. So we caught those. VC, feature, and POGO. We still don't know what those necessarily are. At least we have some names for them. Okay. This might be what we need. But we don't know. Okay, that's an int32. So this has been incremented a billion and 300 million times, almost 1.4 billion times. I don't know if that, I don't think I've compiled 1.4 billion times. Sorry to say. This is so useless. How big is the data? Okay. Let's try to go back and see if we can get... So it seems like the answer is there's 24 bytes there. I don't know. I don't know how I'm going to figure out what those 24 bytes mean necessarily. Three 33100. RSDS. Could it be? So this says 57 bytes. So here's 16, 32, 48, 50, 52, 54, 56, 57. There we go. Again, end of the PDB after 24 extra bytes. PE dump 61 builds. 500-ish. 200-ish for that one. So it could be that the last 4 is the iteration number and that the first 20 are some kind of GUID. All right, there's no guarantee that they would line these up. They're not showing us the structure layout. 4, 6, 8, 16. So it could be RSDS is the magic number or something like that. And then 16 bytes of it are a GUID. And 4 bytes of it are a counter. It's hard to know. It's hard to know. Okay. So I think what we'll do is just for now, we're going to add in one other idea here, because once we've got debug directories, we're going to try and find the PDB path. There we go. There we go. So I think that's good. We have some open questions here. Let's drop these into pe.h. To-dos here include: can we gather information about debug info types besides code view? What are the first 24 bytes of the code view data range? But that seems good for now. We've got far enough to get what I'm going to need short term. All right. We're not doing bad. We're not doing bad. We found a few things new today. Let's look at what comes after debug in the list here. Also, let's look at, let's go back to the one we're actually focused on as our test case. Look at the dump, look at the directories, debug we got. So the next one is TLS table. Yeah, I'm using my own forcoder. This is like default forcoder. I don't have any custom, like since I built forcoder, the default is the one I like. I mean, some of the customizations people have made are super wicked cool, but I'm a kind of a minimalist, so I like the one without all the fancy features. Works pretty well for me. Let's so that's true. I'm not doing forcoder anymore. I'm done with it, but there is a community of forcoder users. You know what I haven't done yet is I haven't gone and gotten like a good invite link to the forcoder Discord that I can share. On Discord, there's a forcoder server that I started, and initially I ran that as just a way to give people info about it, but there's a community fork that they maintain. I mean, you know, people, it's semi-active. So the community fork has a few key fixes that people wanted for a long time, like raises the cap above 30 FPS and stuff like that. Sure, let me go track down that link for you then if you're interested. I'll get you the forcoder community link. Whoops, let's move this off of here. Okay, here you go. That's the forcoder community Discord, and if you join it, you'll find people there are still active enough to help with any issues and things like that that come up. And there's a community fork that is, you know, there's a public chat channel where folks discuss that and have links to it and stuff. So you can go and use it. You could even contribute if you want. That's all like volunteer based now, I think. I don't think they've got like a super organized plan for it entirely, but it's cool. But yeah, no, I put in 5 years on forcoder, and I was definitely, you know, if I put in 5 years now full time on an editor, I would do more with it. But that was about as much as I could take of that one project. 5 years is kind of like, I also put 5 years on the rad debugger. It seems to be my sweet spot. So, you know, we're doing this for Mr. Fourth Lab thing now. working on projects like what I'm doing today and the base layer and stuff, other stuff, and I'll have more than just this that I want to get to someday too. But hopefully I have the ability to churn projects in here in a way that keeps me interested for more than 5 years. But if I get to the end of Mr. Fourth Lab after 5 years, that wouldn't be too surprising either. Right? There's some sort of 5 year like time horizon where I can focus on a particular project and then I have to move on. All right, let's try to wrap up with a Mighty Loop. Yeah, I used to work at Rad. I worked at Rad until, well, technically I worked at Rad until Rad got acquired by Epic, and then I worked there until the beginning of this year, I left so that I could run the Mr. Fourth Lab. But I worked on the Rad debugger for 5 or 6 years. All right. Oh, and by the way, since I was bringing it up, if you want to see my lab continue to put out stuff like what I'm doing right now, well, I put out a lot of free stuff like my streams and my base layer and stuff like that. I rely on supporters, so if you can chip in 5 a month or 50 a year or more, 15 a month, whatever, you help me keep this going. I definitely need more folks join in as members and supporters still. Anyways, the TLS table. Let's see if we can learn anything about that. TLS table. There we go. Okay. The TLS section provides direct PE and COFF support for static thread local storage. TLS is a special storage class that Windows supports. Your data object is not an automatic variable. It is local to each individual thread that runs this code. Thus, each thread can maintain a different value for a variable declared by using TLS. To support this programming construct, the PE and COFF TLS section specifies the following information: initialization data, callback routines for per thread initialization and termination, and the TLS index, which are explained in the following discussion. Executable code access is a static TLS data object through the following steps. At link time, blah, blah, blah. When a thread is created, blah, blah, blah. Yeah, we know about that. The code uses TLS index and TLS array location to get the address of the TLS data area for the given program and module. Each thread has its own TLS data area, but this is transparent to the program, which does not need to know how data is allocated for individual threads. TLS data object is access, okay, blah, blah, blah. Okay, the TLS directory. Let's try putting that over here. We'll put this right here. Close one of my panels, pe.h. And here we go, TLS table, type def struct. So we have 2 different variations of this, it looks like, which is great. TLS directory. Utilities by defining a memory image of the TLS directory and giving it the special name TLS used, or TLS used. Other linker tools for the memory location, TLS directory, blah, blah, blah. When a thread is created, blah, blah, blah. Here it is, TLS directory. PE TLS directory 32. Raw data start, the starting address of the TLS template. The template is a block of data that is used to initialize TLS data. The system copies all of this data each time a thread is created, so it must not be corrupted. Note that this address is not an RVA, it is an address for which there should be a base relocation in the relocation section. Okay. Raw data start. It's not a VOF. It is more like a VAdder. raw data end vadder. The location to receive the TLS index, which the loader assigns. This location is an ordinary data section, so it can be given a symbolic name that is accessible to the program. So is that TLS index vadder, I guess? It's not, it's just as address. Which could be ambiguous here. It could be a vadder that gets relocated, or it could be a voff. The pointer to an array of TLS callback functions. The array is null terminated, so if no callback function is ported, the field points to 4 bytes set to 0. Okay, TLS callback array vadder. Size of zero fill. The size in bytes of the template. Beyond the initialized data delimited by raw data VA, raw data VN. The total template size should be the same as the total size of TLS data in the image file. The zero fill is the amount of data that comes after the initialized non-zero data. Okay, so we have U32 total TLS size. The 4 bits describe alignment info. Possible values are those defined as image section align, which are used to describe alignment. The other 28 bits are reserved for future use. The 4 bits, 23 through 20. Okay. TLS directory flags get align. It's 4, 8, 16, 20. But I'm just going to do it that way. So the alignments don't have to be shifted down. We store them as shifted up in the... We encode them as shifted up everywhere. Sounds good to me. Okay. Now PE32 plus variant goes U64 here, U64 here, U64 here, U64 here, and then size characteristics 4 bits, 4 bytes, 4 bytes. Okay. Let's see. How are we doing on time? We hit 2 hours. I think that's about as much time as I wanted to spend on this. I need to take it a little easy. I need to write up the, the weekly, I need to write up the weekly devlog for people who support the lab and stuff like that. So I think I'm going to leave it here with TLS partially finished. I'm also just feeling myself losing steam just now. I'm like, I can't. So that was a good stream. Gonna wrap it up here for today. Thanks for coming to hang out and chatting and stuff if you did. And of course, again, I'll remind you that if you like these kinds of projects that I'm doing and you'd like to see me be able to keep going on them, I am relying on people like you to choose to come over to mrforth.com/membership and become a monthly supporter or member. And I think that the perks here are pretty cool. And I'm also looking forward to expanding these as I have time to do so. So come check this out. There's also, not listed here, but one of the great perks is credits. When you spend $5 or $15, every time you spend money on this, you earn credits. So if I ever do release some software that I want to sell from the lab, you can just buy it with those credits. So all the money you spend supporting me, you get to spend it again when I release stuff for purchase too. So I think that it's a pretty good deal, and it definitely helps me chase down these projects that I don't know any other way that they could get done. So consider that, and I'll see you all around the internet in the future. Bye.